Atomic theory is what we're essentially working on. And when we talk about the atomic theory, you recall we started with the John Dalton's atomic theory, and then we listed the postulates of the theory, and I gave you PAMDC. That's what I've always used to remember the Dalton atomic theory. Everything's out of particles, attraction, repulsion forces. So everything interacts by attraction or repulsion forces, movement. Everything's in constant motion at 25 degrees standard conditions. I don't remember if I told you the three modes of motion: translation, rotation, and vibration. So those are three modes of motions of the particles. Translation means going from point to point. Rotation, self-explanatory, and rolling effect, and vibration, oscillation, and place. If you're talking about gases, all three would have a high probability. Get to liquids, you're restricting your translation and your rotation, and probably not vibration. But if you get to solids, about all the thing you have is vibration in the molecular model. So that's something to keep in mind. Velocity is directly proportional to the kinetic energy content, and that can be translated to mean heat content. So if you heated a particle, it would go faster. If you cool it, it goes slower. So that's essentially what it means. And the collisions are perfectly elastic. Remember what that means? Anybody? Nobody remember what perfectly elastic means. What is perfectly elastic? What does it have to do with energy? Remember what I said? Zero energy. Come on, guys. You got a test coming at you. In essence, when two particles collide, in reality they will be giving up heat energy. Okay, and then they reabsorb energy by electromagnetic radiation, which is light. Okay, but that's not taken into account in the kinetic molecular theory and Dalton's atomic theory. He said that they just move around and bump into one another and nothing ever changes. Okay, well that's fine. What did he not do? This is one thing you've got to keep in mind for the rest of the models. He did not propose any structure of the atom. Okay, he had symbols that talked about various atoms, but he never proposed, say, something like a nucleus, an electron cloud, and energy levels, and all those things we're going to talk about as we go along in the models of the atom. So, but Dalton was the first to propose an atomic theory based upon scientific principles. Okay, then as time went on, you had various scientists develop the models of atoms, and we find in this case we're looking at 4: Thomson, Raisin, okay, so in the Thomson model, he visualized a sphere and this sphere was positively charged all the way around. And in the sphere were suspended electrons, like raisins in a gelatin pudding. Well, that didn't last very long. The next model was the Rutherford, shell model. And here he is the first, now this is very important to remember, he is the first to propose a two-part atom. And that, of course, is nucleus and electron cloud. Now, in his model, he did not define the electronic structure like we're going to do today with the Bohr model. But there are three facts that I want you to keep in the back of your mind. Well, let me give you this, and this is also important. It's based upon the gold foil experiment. It's very classic. In which he fired alpha particles at a leaf of gold foil, and he had a photographic screen around the gold foil, and he found that most of it went right through without touching anything. Most of the particles are like throwing a bunch of tennis balls at the wall, and they just go into the next room, just disappear through it. So that's what he was seeing. He saw a few very small off at an angles, and then he saw even fewer that were bouncing straight back at him. And the conclusions are essentially postulates, and the atom is mostly space. Okay? And has a negative electron cloud and a positive nucleus. And the electron cloud was about 0.027 weight percent of the atom, and the nucleus was 99.973 weight percent of the atom. And when we talk about mostly space, I want you to remember 100,000 nuclear diameters equal one atomic diameter. Of course, that's an average over the time. So if you get a problem and it says nucleus is 1 millimeter, well, what's the radius? Okay, well, the diameter is going to be 100,000 millimeters, but the radius is half of that, so don't get caught with that and missing that point. Radius is always half of the diameter. So you have this and times 100,000. So you have 100,000 millimeter diameter divided by 2, and the radius is, say, 50,000 millimeters, and some problems come to you and you might have to convert to yards or miles or whatever. And also the volume relationship, nucleus versus atomic volume. It takes one atomic volume is equal to 1,000 million nuclei to fill one atomic volume, and that's actually 1 times 10 to the 15th nuclei on the average for one atomic volume. So these are some factoids that I give to you and ask you to learn these, because at some point in time somebody's going to ask you for whatever reason to describe an atom. Well, these will help explain the idea about what Rutherford came up with. Well, today we move into the other two models. Okay, now we want to look at the Bohr concentric ring model. Okay, the Bohr concentric ring models requires that you understand a couple of issues here, one of which is electromagnetic radiation. Well, that's nothing more than a big fancy term for light. Light is electromagnetic radiation. And so when we study the Bohr model, it's going to be studied in terms of light emissions that come from the atom. And conclusions are drawn from that. We'll show you in a minute, which we call EMR, electromagnetic radiation variables. And these are wave variables, and so wave variables are speed of EMR, frequency of EMR that we're talking about, and wavelength of EMR, and one more, energy content. Well, all of this evolves out of what we call the color spectrum of light. And some of you may already know the acronym for the continuous spectrum is what it's called. And it's Roy, G, B, I, V. Roy G. Biv. Those are the colors of the rainbow. Okay? And that's red, orange, yellow, green, blue, indigo, and violet. Okay? So these colors are electromagnetic radiation, and the fact that they are electromagnetic radiation is that we have to apply these variables to these colors. And so that's one of the issues we want to talk about today. Well, red light has a certain wavelength and energy content, and orange and yellow and all of them have different wavelengths that give them the characteristic colors that they have. And as those wavelengths change, so does the frequency and energy factors in this change. Okay, so the Bohr model, that these colors that we're looking at are what we call discrete wavelengths. Electromagnetic radiation of hydrogen. This diagram is called the bright line spectrum, bright line emission spectrum. Now, to understand this idea of what's happening, how's the atom generating these specific colors, is the question. That's what we're asking. Does everybody can see that? Understand this, what we will propose is that each of these colors are electron transitions from one energy level to another. So what we have to do is draw an atom, and what we're going to say is that down here at the bottom, this points toward the nucleus, and then we're going to say this is the first energy level right here. This is the first ring. We're going to call that n equal 1. That's the first ring, the K shell. So we're beginning to build the concentric ring model. And then this goes more logarithmic, so you can look in the text and you verify this, but it'll spread out a little bit at the beginning, but then it'll start compressing as you get further up. And then it gets real close together, and so you have to, that's n equals 6 and n equal 7. Okay, now how does this relate to this diagram? Well, you visualize these holding electrons. These are electron orbitals. That is, this, you have a nucleus, and then you've got this concentric ring, and they thought the electron orbited the nucleus much like the planets orbit the sun. Well, we'll find out later that's not exactly the case. But this line is the first ring, and the second line is the second ring, and so forth. Now, if an electron is in a given ring, say here's your electron, it contains a certain amount of energy. What we call a positional energy. So if we have an electron that's in this ring, and what happens is that along comes some EMR light, then this thing will jump out. It'll be promoted to a higher energy level. It's called an excited state. When the electron jumps out of whatever orbital it's in and goes up, electron absorbing energy is called an excited state. It's like the discharge tube. When I turn the electricity on, it glowed purple. Okay, that's putting energy into the electrons, and so they're all jumping out to higher energy levels or higher rings in here. Now, we don't see that, and what we see is when they come back down from higher levels. Some of them go out to 7th level. Some of them go out to the 6th level, 5th level. Some of them go to 4, out to 3, and some of them just jump from 1 to 2. Well, we're going to put our electrons in this configuration right now. And when they jump out, they go up, and they absorb energy, but what happens, they don't leave the atom, they fall back down and give off energy. So if it goes to the 3rd, it's going to drop, and we're going to stop at 2. And the reason I do that, when the electron falls back to a lower level, when they stop on n equal 2, that's what we call the visible spectrum. If it goes on down to n equal 1 from wherever it is, that's called a UV spectrum, ultraviolet spectrum. And there is one that if it goes just to n equal 3, the n equal 3 is the infrared IR spectrum. If it stops on 3, it's infrared. Do remember those. It has a certain fancy name, the Lyman series, the Balmer series, the Prashant series, those kind of things. But if you'll remember IR and UV. Now the thing is, you cannot see the infrared transitions if an electron drops down here. But here you can. And if the electron stops on n equal 2. If it stops on n equal 2, it's kind of like a ball. If I throw a ball or this pin up in the air, it goes to a maximum height, and as it comes down from the max height back to my hand, it's giving off energy. That kinetic energy, as it's falling back down, it absorbs energy, then releases energy, like that. When it releases energy and it stops on the n equal 2, it gives off a red light, and that's what you're seeing. This is an n equal 3 to 2 transition right here. If you have a transition that goes from 4, stops at 2, it will give off the green band. And I think you get the pattern. 5 down to 2, it gives off a blue band. Right there. And it goes from 6 to 2, it gives off a purple violet color. And there is one more from 7 to 2, but that's in the UV range and we can't see this. That transition's not viewable. Now the issue here that is really important in you understanding the nature of their conclusions and what they've done here is, here the rings is like the moon. The moon orbits the Earth at a specific distance from the Earth, and the sun is so many other items, satellites, whatever, will orbit at a specific distance. Well, the first energy level from the nucleus is a specific distance called the radius of that orbital. Then we have another radius, and that's different from 1, and all these are very discrete rings, okay? And the electron, here's the key, the electron is in, say, number 3, and then in number 2. It can live in number 3 or it can live in number 2, but nothing in between. There is no middle ground. It's in number 4 or it's not. That's the issue. Since this, how did they come up with the idea of this? This is a discrete wavelength. If they would stop in the middle, if those electrons would stop in the middle of these lines in here, you would see the entire spectrum. It would just be a blur of color from through the whole continuous spectrum. But that's not what is seen in an atom. What you see in an atom is a bright line which represents specific transitions. This is an n equal 4 to 2 transition. This is an n equal 5 to 2 transition. And this one is an n equal 6 down to 2 transition. It's falling from up in specific. It's in number 6 and then it's in number 2. These are called quantum leaps. When it moves from one position to the next, it's a quantum transition. Light is referred to in what we call energy packets, known as quanta. And in order to understand and apply numbers to this concept, we have to apply the what we call the light variables, wave variables, or the EMR variables, and see how these work. And they're very specific, very easy to understand. Okay, we want to learn how, and there are about 3 or 4 different kinds of problems here that will be on the exam, and I'm going to show you how. And they're very specific, very classic type problems. Well, what we're going to do is we're just going to take a n equals, say, 4, and then we'll take n equals 3, and n equals 2, and on down here we'll have 1. Well, you have 1 down here, n equals 1, and then you've got your nucleus way down there, 1.5 miles away or so from here. we're just going to work with the transitions between the different levels. Okay, how do we deal with that? Okay, light or EMR equations. When we talk about the electromagnetic spectrum and light variables, we have to understand wave concepts. A wave of light follows what we call a sine wave, like that. Many of you have seen that in math classes. This is a sine wave. Okay, the distance from the start to the point out here is called the wavelength. It's symbolized by a little lambda. Okay. Now the height of the curve is called amplitude, and that didn't come in at all, so don't even worry about that. As the light travels, it travels in a certain speed. Speed of light, obviously. Now, speed of light is 3 times 10 to the 8th meters per second in a vacuum. Okay, it's a constant. It's published on your reference sheet and all that. So 3 times 10 to the 8th, 186,000 miles a second. Okay. The wave is oscillating through a minimum and a maximum. And the time it takes to go down to the minimum and back up to the maximum is called a frequency of oscillation. And it's usually vibrations per second. Okay. Some books will use a little symbol that looks like a V. Nu is what it's called. I always use an F, and you see them both ways. Frequency F, I like F because it's, descriptive. Lambda's a wavelength, and then you have the speed of light. So you only have 3 variables here you have to worry with. And what's the relationship between them and the various colors? If you look at the bright line spectrum, ROYGBIV, going from red to violet, you go from a low energy to a high energy. From a low vibration to a high vibration rate. So if we're talking about red light, you would see a slow vibration, low vibration. And you would also see a long wavelength on this end. And then on the high energy end, you have a short wavelength on that end of the spectrum. So when we're talking about red end of the spectrum and the 3 variables, what are they? They're in this, energy, wavelength, and vibration. Okay? So every one of them start with L's, low energy, low vibration, and long wavelengths. So you'd see a red light would have a long wavelength, say for red. And when you look at the violet end, you'd see a real short wavelength, like that. You'd have a long wavelength and slow vibration, and then short wavelength and fast vibration. So how do you translate these into energies? Well, a slow vibration is low energy, and the fast vibration is high energy. So we're going to use this idea of the bright line spectrum from the red being low energy, long wavelengths, like that, to high energy vibrations and short wavelengths. So this is what happens if you want to relate wavelength versus frequency. Okay, so if you're on the red end, you'd have a long wavelength and a low frequency. So that's an inverse relationship. That is, lambda is proportional to 1 over frequency. Okay, so as the frequency goes up, wavelength decreases. Or vice versa, as the frequency decreases, the wavelength increases in toward that red end of the spectrum. So we now have a proportional relationship. Well, it turns out to make this an equation in here now, lambda proportional to 1 over frequency, we put in a proportionality constant. Well, it turns out the proportionality constant that connects wavelength and frequency is the speed of light. It is the constant. So lambda is equal to the speed of light, and we use a c, lowercase c, for the speed of light. 3 times 10 to the 8th meters per second. I think I told you 1 times 10 to the 8th a few minutes ago, but it's 3 times 10 to the 8th meters per second. And times 1 over frequency, excuse me. Like that. And so this gives us the first equation of the electromagnetic spectrum. C equals F lambda. So if you're given frequency, you can calculate wavelength, and if you're given wavelength, you can calculate frequency here. I'll go ahead and develop all the equations because they're really straightforward. If you're on the red end, R-O-Y-G-B-I-V, if you're on the red end, you have long wavelengths and low energy. R-G-Y. And on the violet end, you have a high energy. Like that. The frequency is low frequency. And here is a high frequency. Okay? And so we can relate energy to frequency. We have low energy, low frequency, high energy, high frequency. So that's a direct relationship. So frequency versus energy content of the wave is a direct relation in that relationship. So now we can write this is the first equation. Frequency is proportional to what we call delta E. This is your electron transition right there, delta E. When it falls from one level to the next, it gives off energy right here. It turns out that the relationship is connected by a constant called Planck's constant. F equals H, and it'll have a little bar in it. It's called delta E. Okay? Oh, excuse me, HF. I'm sorry. That should be on the other side. Delta E, sorry about that, is H bar times frequency. There you go. And that's what it is. And this is called Planck's constant. And it's published on your reference sheet. It'll be 6.63 times 10 to the minus 34 joule dot seconds. That's the constant you'll use. So if you want to get the energy given the frequency, okay, You just plug in this number, whatever your frequency given, and you can get the energy that's in joules. Now, what we want to do, this is the second equation. The third equation is when these two are connected together or simultaneous through frequency. So you've got a frequency here and you've got a frequency here. And so when we connect these two, we get the wavelength, frequency, and speed of light in there. So if C equals F times lambda, we can solve for frequency C over lambda. And if delta E equals H times frequency, I can take that and substitute it into the equation, and I'll have HC over lambda. And I don't usually put the mark on it anyway. I just write it out, HC over lambda. So we have three equations now. C equals F lambda, delta E equals Planck's constant times the frequency, and then delta E equals HC over the wavelength. So we need to work problems on each one of these. And there'll be one more equation that calculates energy changes in terms of the transitions that go on. And I'll develop that after the break. So we'll take about a 15-minute break, and then we'll. Now, when you work in the atomic level, measurements are going to be things like nanometers and angstroms and stuff of that nature. So one of the things you need to be able to deal with is converting from nanometers to meters and back and forth. 1 nanometer is 10 to the minus 9th of a meter. Okay, so you want to kind of keep up with that little dimension right there. 1 angstrom, usually you'll see it with an A with a little circle over the top of it, is about 10 to the minus 8th of a meter, like that. So those are pretty common terms. The angstroms and the nanometers are used. Okay, now when you look at a bright line spectrum, you see the lines as I've shown you. What you can measure directly is wavelengths. So when I say this is something you're measuring in the surroundings, in other words, you're the observer, this passes through what was called a spectroscope. And a spectroscope, it will measure the wavelengths in terms of meters, centimeters, and nanometers, whatever is calibrated to do. Now, to get frequency from a wavelength, we use C equals F times lambda and solve that for frequency, which is the speed of light over wavelength. Okay? So in working with wavelengths in this equation, wavelengths needs to be converted to meters. As we go through this. Now, that's pretty straightforward. Lambda, say we're working with the blue wavelength, 434 nanometers times, well, there are per nanometer is 10 to the minus 9th of a meter, like that. So that's 434 times 10 to the minus 9th of a meter. And to put it in standard form, we move back to the left 2 places, and that adds back to the exponent. So that's 4.34 times 10 to the minus 7th of a meter for the blue light. That's the wavelength. Now, if we want to calculate frequency, we have to have the speed of light. Let's see. C equals 3 times 10 to the 8th meters per second. So we're in the same units, and so the frequency is the unknown quantity. So now we can take the equation F equals C over lambda and substitute the values, 3 times 10 to the 8th meters per second divided by a wavelength of 4.34 times 10 to the minus 7 meters, and you'll get units will be slash seconds, and that's interpreted as cycles per second because meters will cancel out. So that comes out 6.91 times 10 to the minus 14 cycles per second. So just to, this is cycles per second, or CPS, and a cycle per second is also known as a hertz. Is 1 cycle per second, HERTZ, like the car rental outfit. Anyway, sometimes this is written in terms of the per second will be SEC minus 1. So you'll see 6.91 times 10 to the 14 seconds to the minus 1. So in problems that you will see, all of those might show up for units of frequency, as you might. Okay, so now we've got the frequency of our wavelength. Now we want to calculate energy from the frequency. So the second equation I showed you earlier was delta E equals Planck's constant times frequency. So Planck's constant, H, is 6.63 times 10 to the minus 34 joule seconds. And we've just calculated the frequency of our blue light is 6.91 times 10 to the 14th slash seconds, if you want to do it like that. And so we simply substitute into the E equals HF equation. Very straightforward, very classic in terms of the problems. You get problems just like this on exam day. So just a matter of learning how to substitute and convert. So that's 6.63 10 to the minus 34 joule seconds. And the frequency is 6.91 times 10 to the 14th seconds to the minus 1, or divided by seconds. And so seconds in the Planck's constant will cancel with seconds over here. And so you're only left with the units of joules. And that's what we want. Okay. So this comes out as 458 times 10 to the minus 19th joule. Now that's the energy given off by that blue light transition, and it's still, and at the same time, it's giving off wavelengths of 434 nanometers. Now, the third calculation out of this series of problems is calculating energy from wavelength. Now, this is essentially the same problem, except the delta E equation will be hc over lambda, and h and c both are constants divided by the wavelength in meters. So delta E is equal to hc over lambda. Now h, again, is 6.63 times 10 to the minus 34 joule seconds. It might be useful to note that a joule, if you want to check the unit cancellations, is kilogram dot meters per kilogram meter squared over second squared. So if you took that and substituted in for the joule, okay, that's what that term can be converted to easy enough. C is again 3 times 10 to the 8 meters per second. Now our frequency, wavelength, with 434 nanometers, and then we multiply it times 10 to the minus and then move the decimal over, we have again 4.34 times 10 to the minus 7th of a meter. Now, whatever wavelength in nanometers, you can get the meters just by tacking on times 10 to the minus 7 and putting it in standard form, the coefficient in standard form right here. Just move the decimal here, and whatever wavelength, like we had the red wavelength is 656 nanometers. Well, put it 6.56 times 10 to the minus 7th meter. Okay, all of them will do the same thing. Okay, you're not going to have something that's slow as a water wave or something like that. Everything's going to be this on the test. So when you make your conversion, it's just a real, neat thing. Just put times 10 to the minus 7 and put coefficient in standard form. So that's an easy conversion for you. Okay, substituting, we get essentially the same net number. Delta E equals 6.63 times 10 to the minus 34 joule dot seconds. That's your Planck's constant. 3 times 10 to the 8th meters per second for that one. And that's divided by 4.34 times 10 to the minus 7th of a meter, and will give you the same energy number that we got a while ago, 4.58 times 10 to the minus 19 joule. And that's the blue light. Okay, and that's all I did. Now you've got 3 other colors involved, the transition colors. I did the one for blue, and the one for green, frequency, wavelengths, and energies, and every one of them are calculated the same way as we did for the blue, and then you do the one for the red. Because when I give you the exam, I'm going to ask you one of those. Okay, so it should be an easy calculation for you. Just kind of keep up with the numbers as you put things together. Okay, this next section is known as the Rydberg energy and wave equations. Okay, guess that's readable. Anyway, what I'm about to develop for you and show you is equations independent of the what we call the light variable EMR equations. Remember, the delta E equals hc over lambda. We calculate an energy. Okay, delta E equals hc over lambda, which is h times frequency. Okay, so this is the energy of transition. That's what. Okay, so if it goes from 3 to 2, we can calculate it. If we've got the wavelength measured. Now, what Niels Bohr and his associates did is they determined what the energy of the electron is, energy content, or potential energy of the electron while it's living in that energy level, and the energy while it's living in this energy level. Okay? Well, it turns out the equation for energy in a specific level, E at whatever level N that you have, this is potential energy content. So that's the potential energy content while it's living in it. It's like a something sitting on a shelf, and then it falls off the shelf. It's at a lower energy level, it's the second shelf down or so. And so E, well, the equation for this is equal to a minus A, which is a big constant, I'll show you, over N squared. So you can calculate the content, energy content, and A is equal to 2.18 times 10 to the minus 18th of a joule. It's a real easy equation. So if you want to know what the energy for N equals 3 is, that is minus 2.18 times 10 to the minus 18th divided by 3 squared, and that'll be in joules. Let me move that out here. That. Okay, that comes out 2.42 times 10 to the minus 19th of a joule. That's what it's holding while it's living in energy level number 2. All right, calculating the energy level in number 3 there. Number 2 is equal to minus, same thing, 2.18 times 10 to the minus 18th over 2 squared joules this time. Now that one comes out 5.45 times 10 to the minus 19th of a joule. Okay? So if we know what it is in n equal 3, and we know what it is now in n equal 2, how do we get the change in energy now? E2 minus E3 energy levels, okay? So that's taking the difference in these two and seeing what that energy is. So that'd be 5.45 times 10 to the minus 19th minus 2.42 times 10 to the minus 19th. As it's falling, it's always exothermic. Going up is endothermic. But always come out, whether you calculate it right, the difference in the two gives you the number, energy number, but it's always, you put a negative on it, always, because it's falling. And so that gives us the difference in these two, E2, is 3.03 times 10 to the minus 19th of a joule. And that's called the transition equation. And you could simplify the transition into one little equation. I'll show it to you. If you want to calculate the in transition energy, it's A onto 1 over n squared initial minus 1 over n squared final, like that. It's simply taking this equation and substituting final and initial and taking the difference in the two and solving it algebraically. Okay, that's all it involves, is taking that equation right here and saying, well, one of them's final and then one's initial, and you subtract the two and you'll get this equation. And so it's a real simple, it's called the Rydberg energy equation. Okay? Note that this is in terms of the transition alone, only. Very important note here. I'll show you why in a second. Okay. So we'll kind of keep that 3.03 times 10 to the minus 19th joule calculated using this. I'll jot that down here. Delta E from a 3 to 2 transition is 3.03 times 10 to the minus 19th of a joule. As it's falling from 3 down to 2, it gives off red light. Okay, now calculate the energy as I showed you using HC over lambda now. Okay, this is in terms of a measured wavelength right here. Okay, so that's 6.63 times 10 to the minus 34 joule seconds times 10 to the 8 meters per second divided by the wavelength of the red light is 656 nanometers. So I put the decimal in standard times 10 to the minus 7 of a meter. Well, when you punch this into your calculator, it's going to come out identical to what we just calculated using the Rydberg equation. Except this one is, this calculation here, the second one I just did, is in terms of the EMR equation. Well, everybody knew that. Okay? This is what's new using the Rydberg energy equation. He proved that the transition produced the same energy. And so the concentric ring model grew from that. And so this is the first transition. And then you can calculate any transition that's up there. Right? It comes up and says, okay, calculate delta E for an n equal 5 to n equal 2 transition. Okay, that's one type of calculation. Or calculate delta E for green line of hydrogen gas spectrum. And they'll give you the green line is 487 nanometers. Okay, in the first case, you'd have to use the Rydberg equation. Delta E equals A on to 1 over n initial. Now, see, the equation solves out to be initial final squared like that. In the second calculation, delta E equals hc over lambda. Okay, so you calculate it from the given wavelength in there. So these are two that you need to learn how to solve, because they're going to be repeated. And just like we've done, I've really worked them out for you in the context of this equation. Okay, so if we have the delta E equals A on to 1 over n squared initial minus 1 over n squared final. That's the delta E. And we also know that delta E equals hc over lambda. So I can put these two equal to one another. These two equations equal. And it'll look like this. hc over lambda is equal to A on to n squared minus 1 over n squared initial final. Just like that. So I just scribble it out. It's just so familiar. And you can learn it just like that. 1 over n squared, 1 over n minus 1 over n squared. Initial final, put an A in front of it. Now, if I'm interested in calculating the wavelength, what I do is divide both sides of this equation by h times c. And so if I divide both sides by hc, I get 1 over lambda is equal to A over hc, 1 over n squared minus 1 over n squared initial final, just like that. Turns out this is a constants. It's 2.18 10 to the minus 18. There's Planck's constant and speed of light. Well, this expressed in what they show is in the textbook. Most textbooks will publish this. Turns out that A over hc, when you work it out, is 109,678 centimeters to the minus 1. This is published on your reference sheet. You don't have to look it up. Okay, and this is usually listed as R with a little h subscript like that. It's called the Rydberg energy equation for the hydrogen transitions. Okay, it's just RH. And so this equation would look like this. If I put the R for the A over HC, I'd have RH 1 over n squared minus 1 over n squared initial final. Like that. So you can calculate the wavelength from a transition. All right, we'll take a look at that real quick. Let's see, calculate lambda for 5 to 2 transition. Okay, so 1 over lambda is equal to RH n squared minus 1 over n squared initial final. So this is, we're given the R, you got that, okay, and then they just gave you the transition, you substitute those, and you work this out, and you'll get a reciprocal number, reciprocal centimeters. You take the reciprocal, get it to meters, and then convert to meters, it'll be the same wavelength as a 5 to 2 transition, the blue line. So this is 109,678 centimeters minus 1. And incidentally, you can actually, this is the slope of a certain kind of graph. It's really easy to derive. Initially, you're at 5 squared minus 1 over 2 squared. And so this is 109,678 onto 1 over 25 minus 1 over 4. Now, it'll come out negative, but just, you know, you don't have negative wavelengths, so just change it. Okay, it's just the way the equation works. Okay, and you drive yourself crazy worrying about pluses and minuses. If it's going up, it's add. If it's coming down, it's negative. That's all it is. Okay, so numbers on this is going to come out in reciprocal centimeters, 23,032, 1 over lambda. Well, you want to get that to centimeters, so you solve for lambda, you just switch places with them, and you have 1 over 23,032, and this will be in centimeters. Okay, and if you want to go to meters, centimeters, meters is 100 centimeters in a meter, and so that's a 5 to 2 transition, and I bet you Buffalo nickel is 434 nanometers, 4.34 times 10 to the minus 7th of a meter, which is 434 nanometers, and that's the blue line. Very classic type calculation. Now I'm going to summarize all of this for you and let y'all get a chance. Here's all of them in a nice little package for you. Okay? So you'll have problems which will deal with, well, calculate the frequency given the wavelength, or calculate wavelength given frequency. So that's one set of problems right there. Calculate energy given frequency, or given frequency, calculate energy. So back and forth there. Calculate energy given wavelength, or given wavelength, calculate energy. So you use that. So this is the EMR equations, and of course these will be published in the reference sheets. Just look back. You don't have to memorize a bunch of constants. Then we go into the transition equations. These are the Rydberg equations, energy equation and the wave equation. And it's A onto 1 over n squared minus 1 over n squared initial final. Same way with this one, 1 over n squared minus 1 over n squared final, initial final. But you substitute the R value, and it comes out centimeters. But remember, you got to convert this to centimeters and then back to meters. The first one just goes straight to joules for you, but that's it. Those are all classic Bohr model problems. Now, the actual math and everything that goes into this is light years away from what we would do in this level. So this is all you need, and this will serve you for all the standardized tests you can take. Okay.